So we have introduced three main methods that we will study and apply to different situations for solving the redundancy in robot manipulators. We mentioned the Jacobian-based methods, so that are only based on the Jacobian, the analytic Jacobian of our task direct kinematics. Null space method that will use self-motion in order to accomplish some extra objective, and task augmentation method. Last time we started looking at the minimal requirement for Jacobian-based method. We mentioned that we are looking for a solution of the form q dot equal k of q r dot, where r dot is the desired velocity. This is a local method, so it's the desired task velocity at the current configuration q. So this is a transposed matrix of the original Jacobian in terms of dimension, n rows and m columns. And of course we cannot take any k, but we have already seen one possible choice. We have a minimum requirement for the k to be a generalized inverse of the Jacobian j. And this is the condition that any k should be satisfied in order to be used in this inversion problem. And the reason why this is required is because if we are assuming that r dot is realizable in that configuration, so it belongs to the range of the Jacobian matrix, then this requirement guarantees that we return with any k satisfying this condition the desired r dot. And one example, and we stopped here last time, was this type of partitioned solution. This k satisfies indeed the property, and having a 0 here means that we are doing what we don't want to, really don't like too much actually. Namely, we are zeroing the motion of the redundant degrees of freedom. Once we have found out a minor which is non-singular, the JA matrix, the other joints do not move because the velocity is set to 0. Okay? So, but the most popular choice of k is probably the use of a pseudo-inverse. So this is a particular k, so it's at least a generalized inverse, but this matrix shares much more properties as we already introduced in Robotics 1. Now we will see back this condition. So the pseudo-inverse of a given matrix J, no matter if it's a square matrix or a rectangular matrix, like in this case with less rows than columns, but the concept applies also to the case of more rows than columns, as we have seen in the problem of calibration. We have solved the calibration equation by pseudo-inverting a tall non-square matrix, while in the case of redundancy we have fat Jacobian with more columns than rows. So no matter how many rows and columns have the J, the pseudo-inverse of this matrix always exists, is unique, and in fact it's the unique matrix that satisfies this for definition or defining problem conditions. And you can recognize that the first condition is nothing else than the one that we have imposed to a generic k, so being a generalized inverse of the matrix. But in addition, we require also that the other second relation, J pseudo-inverse times J pseudo-inverse, returns the pseudo-inverse itself, and the fact that the product of the matrix times its pseudo-inverse and vice versa is a symmetric matrix. The two last equation specify this. So there are situations in which you can give an explicit form to the solution or to the pseudo-inverse. In particular, if we have that the J is full rank, in our case full row rank, then the pseudo-inverse takes this form. Pay attention, this is exactly the complementary version of what we have seen for the calibration problem. In that case, we had the opposite situation. But we have an explicit form. And you can immediately see that under the assumption of full row rank of J, this matrix JJ transpose is certainly non-singular, so we can inverse it. And we pre-multiply it by the transpose to get the pseudo-inverse. If we don't believe that this is the pseudo-inverse, we have just to check the 4 defining equation. In fact, if you pre-multiply this by J, so you take the first condition, you have JJ plus, it's JJ transpose times is inverse, this is the identity. Which means that if you post-multiply by J, you return J. If you pre-multiply by J pseudo-inverse, you get J pseudo-inverse. And similarly, the identity is symmetric, and even if you do the product J pseudo-inverse, so this and post-multiply by J, so you're constructing this 4th condition, you will see that you take the transpose, you obtain the same matrix, so this is symmetric. Since this satisfies the 4 defining equation and the pseudo-inverse is unique, this is the pseudo-inverse. Pay attention because this type of reasoning is very useful also for more general cases. Okay. Now, what if we don't have full row rank? And this is a very critical situation that is encountered many times when we are dealing with redundancy and also without redundancy. The pseudo-inverse still exists and is unique, but has not this explicit form. It needs to be computed numerically, and this computation is done by using the singular value decomposition of the Jacobian J, and we will see in a moment what this means. You can use a routine, for instance, in MATLAB. The function pinv, pseudo-inverse, is there, and inside the function there's a call to another function which does the singular value decomposition of the Jacobian. Okay? And once you have the singular value decomposition, the pseudo-inverse is very simple to compute. Now, what is why this matrix is so popular in redundancy and not only, is because the solution that we get, the joint velocity that we get, minimize the norm of any velocity which either satisfy the original task, so such that J times Q dot is equal to R dot, so the task in velocity, or if this is not possible, minimize the norm on the task velocity error, so the difference between J Q dot and R dot. In fact, there may be more velocity that minimize this without bringing it to 0, because R dot does not belong to the range of J. And among those, if you compute Q dot with a pseudo-inverse, you're guaranteed that you get the one with the smallest norm. So the smallest velocity in order to perform the task, which is a very nice property in general. Indeed, if the task is feasible, so if R dot belongs to it's not unequal, belongs to the range of J, then there will be no task error. So this norm will be 0, okay, automatically by the choice of J. Now, there's one first warning that I should give you. When we're dealing with norms in general, no matter if they are in the joint space, like for this velocity, or in the task space, imagine that this is a linear velocity of the end effector, so a 3-dimensional vector. So no matter which space we are working with, if we have quantities that are non-consistent in units, for instance, we have a prismatic joints and we have revolute joints, or we're considering in the task space some linear quantities and some angular quantities, the concept of minimum norm is ill-posed, because we are comparing, in fact, as we like to say, apples and oranges. So if you have a linear quantity and an angular quantity in the same vector, then you don't know if 1 meter per second has the same weight of 1 radian per second, or 57 degrees per second, or 100 centimeters per second. Okay, so these units are not compatible. So minimizing the norm over non-consistent vector makes no big sense Nonetheless, this is being done over and over. Sometimes, we will see, we introduce some weighting to take into account of this inconsistency. But putting aside this warning, let me just, to be confident, more confident, do some computation of pseudo-inverse for few very simple cases. Cases that I can treat by hand without resorting to MATLAB or to a program that does this. So let's start with the first simple example. Suppose that your matrix J, remember this is the Jacobian of the task that you are evaluating at a given configuration, so it becomes a matrix of number. Suppose that you have a one-dimensional task and 3 joint velocity. And the J matrix, so it's a 1 by 3 matrix. Let's put some numbers, 1, 2, 3. No big fantasy. Now, as this matrix full rank, certainly yes. As soon as one element is different from 0, this has rank 1. So I can use the general formula. So I can write that J is nothing else than 1 over the sum of the square of this, so it's 9 plus 4 plus 1, so it's 14, and then the same matrix transpose. So this is J transpose, and this is J transpose to the minus 1, which is nothing else than a scalar and the inverse of a scalar. So I can put it in front. Okay? Well, let's do a second example. Now I'm taking a square matrix. So I'm not talking about redundancy, but sometimes we will see that we square the Jacobian by adding additional task and adding additional rows of an augmented Jacobian. So this may be the case. And suppose that we are in a situation, let's put, of this kind. So the difference between here and here is that this is full rank. This is square, but we don't care too much about this, but has not full rank, as you can see. Still, the pseudo-inverse, it's very easy in this case, is 1/3, 0, 0, 0. Do you believe me or not? If you believe me, we go ahead with a third example. If you don't believe me, like you should, you just try and check out this for condition. And you will find immediately that J times J pseudo-inverse, first row times first column is 1, first row times second column is 0, second row times whatever is 0, 0. So it's not the identity like in this case, but it's in fact a part of the identity. And all the other terms are 0. The fact that zeros reproduce zeros, which is completely different than in inverses. If you're taking the inverse of this, you will have approximately 1/3 and 1/0, so infinite. Okay, so if this is not 0 but it's epsilon, and epsilon is going to 0, the matrix can be inverted, but the inverse has huge numbers. Okay, and this is a numerical problem. So the fact that you replace zeros with zeros, it's intuitively suggests that we're trying to keep low our solution in terms of norms. Okay, this is just qualitative, of course. Now let's move on. Let's do a third exercise. The third one is a modification of the first. So suppose now that I have a 2 by 3 matrix. So the task is 2-dimensional, like for instance positioning the end effector in the plane for a 3R arm, no matter if 3 degrees of freedom arm, which is planar, no matter if the joints are all revolute or a mix of revolute and prismatic ones. And suppose that the first row evaluated in the given configuration is again like the first example, and the second row is 0, 0, 0. Now, can you guess the pseudo-inverse here? the result is rather a combination of these two situations. Well, I'm writing it, and you may not be surprised. The pseudo-inverse is simply this one. Okay? And again, you can check that J pseudo-inverse is 1, 0, 0, 0. Okay? And then using this into those equation, you can check that this, in fact, satisfies the 4 conditions, so you have completed. And now the final, let me cancel this. The final example is, again, a 2 by 3. So I'm taking 1, 0, 2 and 2, 1, 1, or better say 1 minus 1. Okay. Now, the first thing that I have to check if I want to perform computation by hand, like I'm doing here on the blackboard, I check if this has full rank. How do I check the rank of a non-square matrix? I'm waiting for suggestions.
We can do some computations for echelon.
We can do some computation, definitely. But which computation? In fact, your colleague suggested it right. So we look for minors. There are, I mean, to have full rank, meaning 2, it means that there should be a 2 by 2 submatrix extracted by columns and rows. In this case, I have to take both rows, and either I take out this column or this column or this column. So I have 3 potential minors, and this should be different from 0. So the determinant should be different from 0. If at least 1 is different from 0, we have a full rank matrix. And this is one way. The other way, sometimes easier, sometimes more complex if you have symbolic expression, is to compute, to build the matrix J transpose, which will be a square matrix, and to compute the determinant. And the determinant will be equal to 0 if and only if the original J matrix loses rank. Okay, these are the 2 standard methods for doing this computation. Now here we can see immediately that this is full rank. For instance, the first 2 rows, this minor has determinant minus equal to 1. So I can use the general formula. So I can write, I can do this computation, and the final result is 1/5, 0, 2/5, and then 1/3, 1/6, and minus 1/6. And the fact that you have these numbers comes exactly from doing first the computation J transpose. It's a 2 by 2 matrix. By the way, it's a diagonal 2 by 2 matrix, so the inversion is very simple. And then you multiply, you pre-multiply by J transpose, and you get the result. Okay? So you should not be scared from that. If you have a more complex situation, of course, you will use the pseudo-inverse, but look at the result if this makes sense or not. This is always a basic aspect. Okay, so what else? We mentioned a problem of inconsistency if we have different units in the joint space and or in the Cartesian space or in the task space. But apart from this, we may wish in our solution to give more weight or to prefer a joint velocity which has a reduced value for some selected joints. For instance, we mentioned if you want to move a long chain of bodies by a small amount, we may prefer to move the farthest joint in the chain rather than the base joints, because this would mean moving all the masses involved, although we are considering only a kinematic problem. But physics intuition says this. So if we want to tackle this problem in a formal way, we may choose among the possible K-matrix, so among the possible generalized inverse, not the pseudo-inverse, which makes no difference between the single joint components, minimize the norm without weighting, a weighted pseudo-inverse. Okay? So what is this? Well, again, we have a nice explicit form if the J matrix is full rank, in particular full row rank. So the weighted pseudo-inverse of the matrix J, if W is a positive definite matrix, and this is our requirement, many times we choose W as a diagonal matrix, so with positive elements, so certainly invertible. So it's W to the minus 1, J transpose, and then again J W to the minus 1, J transpose minus 1. And you can immediately see that if W is the identity matrix, we resume the original pseudo-inverse. Okay, so this is a natural generalization of this concept. Of course, if the matrix J is not full rank, you cannot use this formula, because this second matrix is not invertible. Well, actually, you may still use this expression, but instead of doing the pseudo-inverse, the inverse of J W to the minus 1 J transpose, you can do the pseudo-inverse of this matrix. And then you get exactly what you need for. Okay? So this is one way of doing things. Now, has this pseudo-inverse, weighted pseudo-inverse solution some property in terms of minimizing a norm? Yes, the solution Q dot minimizes this weighted norm. So the norm of the velocity weighted by the matrix W, the square norm. So the square norm will just be Q dot transpose Q dot. Because there's a weighting in this norm, we have the W, and this is why we are requiring W to be positive definite and symmetric. Remember that in a quadratic form, if the matrix was not symmetric, only the symmetric part counts, because the skew symmetric one, so what is missing, vanishes in a quadratic form always. Okay, and often we choose W as being diagonal. So this solution, we know that this solution minimizes this norm. So the question is, how do we choose W? As we said, if we just stick with the diagonal W, it's not required, but this is then very clear what we are doing. We will see that when we attack the problem from a dynamic point of view, we will use weighting that are not diagonal, but still positive definite. So for a diagonal case, a large weight on the diagonal in position I means that I would prefer not to use that velocity, or I will use that velocity the least possible in such a way that I can guarantee to execute the task. So there's a inverse proportional relation between these two situations. So I can, of course, how large, doesn't matter. Doesn't matter because we are not interested really in the value of this objective function. We are interested in shaping the solution Q dot. So if you're using a weighting which is 100, 100, 100 for the three joints, it's like using no weighting at all, because we make no difference between the joints. So it's like the solution will be exactly the same as we are using W equal 1, 1, 1. So we have to discard this balance. And if we choose a 1, 10, 1, then typically we will move less joint 2 with respect to joint 1 and joint 3 in executing the task. So one situation, which is very nice. By the way, it was just last exam included this question, is when you have joint limits. Now, suppose that joint I lives in an interval, qi min, qi max. And those two values, of course, min is less than max, but maybe both positive, both negative, one positive. You could have a symmetric joint range, which means that, for instance, you have a revolute joint that can move between minus 60 degrees and plus 60 degrees, or in an asymmetric way between 10 degrees and 55 degrees, something like that. Of course, the smaller is the available joint range, and this available joint range may be the mechanical one. So it may, due to the construction and assembly of your manipulator, or may be imposed by some additional restriction that you have given to the robot because of the presence of, for instance, obstacles. Okay? No matter what, if this interval is small, of course, the velocity that you compute here for executing the original task, you would like that to have a small joint velocity here, because large joint velocity are likely to move the configuration out of this range, because the range is small. So in this case, you can use as wi just 1 over qi max minus qi min, and if you wish, you can add the square, but certainly this will be a positive number anyway. Okay? So the smaller the range, the higher the weight, and the less you will move the associated joint. Okay? Now, pay attention. Although it's called weighted pseudo-inverse, although it seems to generalize the concept of pseudo-inverse, in fact, it satisfies less properties than the pseudo-inverse. We know that the pseudo-inverse is unique, so if we are weighting it, then we cannot find something else than the pseudo-inverse itself. In fact, this matrix, the weighted pseudo-inverse, satisfies 3 out of the 4 defining conditions of a pseudo-inverse. In particular, look at this full rank case. If you pre-multiply this matrix by J, you get the identity. So automatically you satisfy the first 2, and you have the symmetry for J pseudo-inverse weighted. But if you post-multiply this by J, this matrix in general is not at all symmetric. If you take the transpose, you will get a completely different matrix. So the 4th condition is not satisfied, unless W is the identity. In this case, this boils down back to the pseudo-inversion. Okay, so now a bit of mathematics. Since we have dealt with cases, also elementary cases, where we can compute explicitly the pseudo-inverse, but most of the time we have to resort to a numerical computation. And we just mentioned that this is associated to the decomposition in singular values of the Jacobian matrix. This is a general concept, as we said, that applies to all matrices, no matter which are their size, square or non-square. So what is this? The singular value decomposition, again, it's a numerical procedure that, given a matrix J, I'm using J because this is what is of interest, produces 3 factorizing matrices such that J is given by the product of these 3 matrices, U, a sigma, and a V transpose. Now, U and V are square matrices. U has the same size of the rows, of the number of rows of J, so M by M, and V has the same size of the columns of J, so N by N in our case, and these 2 matrices are orthonormal. Okay? They are computed numerically, but they have this property. You remember what the orthonormal matrix is? Or what are the properties of orthonormal matrices? So the inverse is equal to the transpose. The column and rows are unitary vectors and are orthogonal each to the other. So, for instance, you can use U or V as a basis for its space, because the columns are, in fact, linear independent and span the whole set. Okay. Now, the characteristic aspect is what is in between, this sigma matrix. Now, if the J matrix is fat, like in the redundant case, then this matrix will have a diagonal part as a first block, so an m by m diagonal part with listed the so-called singular values of the matrix J. Sigma 1, sigma 2, up to sigma m, and the remaining part will fill the difference between the n column and the m row with zeros. Of course, if you had the opposite situation, so a tall matrix, the sigma part would be on top and the zero would be at the bottom. Okay, this is the only change. So now look at the sigmas. The sigmas are ordered from the largest one to the smallest one. They are all non-negative, differently from eigenvalues of a generic matrix. Remember, if a matrix is symmetric, is square and symmetric, it has eigenvalues which are real, but not said they are all positive. If a square matrix is symmetric and positive definite, all its eigenvalues are real and positive. Now, this is a slight generalization to the case of a non-square matrix. So they are ordered, and the nice thing is that the largest is, let's say, positive, and then when you go down and you stop at a certain index rho, which is less or equal than m, then this index rho is exactly the rank of the matrix. So if you have a 3 by 8 Jacobian, then you will have 3 singular values, sigma 1, sigma 2, and sigma 3. And if sigma 1 is positive, sigma 2 is positive, but indeed smaller than sigma 1, and sigma 3 is 0, then the rank of the matrix is 2. Okay? So, in fact, this is the way in which MATLAB, for instance, provides you the answer to the question, what is the rank of this matrix? It does the singular value decomposition, and then check which is the smallest singular value which is still positive. And the index of this singular value will be the rank of the matrix. Okay? So, now, many properties with singular values. The first one is the following. And we will prove it now on the blackboard. So if we take the columns of the orthonormal matrix of this factorization, this will be eigenvector of J transpose associated to the non-negative eigenvalue sigma I square. The second property is that the columns of V, the second matrix which is transposed beyond, are the eigenvector of J transpose J, of the inverse. Now let's do this check. So we start from J equal U sigma V transpose with the definition that are on the slide. Now we compute J times J transpose, because our first statement, the only one that we will prove, the second I will leave you as an exercise for you, says that the columns are eigenvectors of this matrix. So let's build the matrix first. So this is U sigma V transpose times the transpose of this. So I have to transpose, change the order of this and have this type of expression. Okay? Now, V transpose times V is the identity, because V is an orthonormal matrix. So this is the identity, so we end up with U sigma times sigma transpose. Let's look at this expression. You have a diagonal matrix, zeros, and then the transpose of it, which is diagonal matrix 0. So the 0 doesn't count, and you have a diagonal matrix times the diagonal matrix. So here you can write this DIAG of sigma I square, and this is an M times M matrix, and then you have U transpose. Okay, so these are the product of three matrices which are all M by M. Okay. Now, let's take the next step is multiplying this by one of the columns of, so U has columns, U1, U2, UI, UM. So let's take a generic column I and do the product J transpose times UI. So we are multiplying a matrix by something that we suppose to be an eigenvector. This matrix is symmetric, so we expect a real eigenvalue. If this is the eigenvector, then we will find a solution which is the eigenvalue times the same vector. Okay? So if we do this computation, we have U diagonal of sigma I square, U transpose times UI. Now this product here, can you guess the result of this product of an M by M matrix times a column? Well, the U transpose is U1 transpose, U2 transpose, UI transpose till UM transpose, so the transpose of these columns. But these columns are orthogonal to each other. So if I have a UJ transpose times UI, I will get 0. And the only thing that is non-zero is the product UI transpose times UI, which is 1. So this is nothing else than 0, 0, 1 in position I, and then 0 again. And if I multiply this by this square matrix, and this matrix is diagonal, the result will simply be 0, 0, sigma I square, 0, in position I. Okay? Now we are almost done because we have U times this vector, which has only one non-zero element, which takes out of this matrix just the ith column. So the result is sigma I square times UI, the ith column of U. And this shows that UI is an eigenvector. In fact, if I multiply A by this direction, I get the same direction, but scaled by a factor, and the factor is nothing else than the positive eigenvalue, sigma I square of J transpose. And sigma I square is the square of the singular value sigma I of the original matrix J. Okay, and exactly in the same way you can prove also the second statement. And even more interesting, with the columns of V, you can build a null space, a basis for the null space of matrix J. Remember, the null space are, in our interpretation of this matrix, being J the task Jacobian, so our joint velocity Q dot such that J times Q dot is equal to 0. So all possible joint velocity which are in the null space, and we will see that this will be used for doing some extra task, using redundancy to do some extra task or to pursue some other objective rather than the main task. So a basis for this null space is given exactly by the columns. In fact, the last n minus rho, where rho is the rank of J, columns of the orthonormal matrix V. So the columns are certainly bases, but this subset of columns is a basis for a special subspace, which is the null space of J. So it's a very important because we will use this in numerical computation. Of course, this computation is hard to be made symbolically. Even if you're using the MATLAB symbolic toolbox, you can do determinant of symbolic matrix, but you cannot do the singular value decomposition of a symbolic matrix. If this matrix is small, let's say 2 by 2, 3 by 3, you can do this by hand, but otherwise you can only work numerically, okay? So, and with this in hand, again, some homework for you. Please take what we have said so far and show that the pseudo-inverse, in fact, this is the reason why we are introducing the singular value decomposition, of matrix J can be computed very easily from the three matrices that does the factorization of J. In fact, J pseudo-inverse is the two orthonormal matrix exchanges of position and transpose, so V and UT, and in the middle, the pseudo-inverse of this special sigma matrix, which is nothing else than transposing the matrix, putting the 0 at the bottom, and inverting the singular values which are strictly positive, so sigma 1, sigma 2, up to sigma rho in general, and leaving zeros for the singular values which are 0. Okay, so again, same idea that we have seen in the simple example that I presented on the blackboard. So this is true for any rank. If J has full rank, and you don't need to do this computation in that case because you have an explicit expression for the pseudo-inverse, J transpose times J transpose to the -1, but you may still wish to do the computation in a general sense, then the element on the top part, diagonal top part of the pseudo-inverse or sigma are 1 over sigma 1 until 1 over sigma m, because all the singular values are strictly positive, so they can be inverted. The other property that we have seen, not really on the weighted pseudo-inverse, in fact, is that you can formulate a linear quadratic problem. We will see this more in general later on. But in this case, it's nice. If you want to minimize the square norm of the joint velocity weighted by a positive definite matrix W while satisfying this constraint, and suppose that J has full rank so that R dot will be certainly in the range of J, then solving this problem with Lagrange methods of optimization, you will get exactly the pseudo-inverse, and of course the case of a the weighted pseudo-inverse, sorry. And of course the case of a pseudo-inverse is nothing else than the same case with W equal to the identity. And finally, I already anticipated this, how do you compute the weighted pseudo-inverse when the Jacobian is not full rank using the singular value decomposition? You can do this with the formula that I anticipated, but this is another way of doing things. You first take the half of the inverse, so the square root of the inverse of the positive definite matrix W, and you compute an auxiliary Jacobian, post-multiplying by this. Then you do the pseudo-inverse of the Jacobian, and you pre-multiply by W to the -1, and you get the weighted pseudo-inverse. Okay, so you can use the same routine pin for doing the job. Okay, now a small break. Small break that brings together many things that we have seen so far, and also that we saw in Robotics 1 when dealing with inversion of a square Jacobian, when we were getting close to a singularity. Same situation here. When we're getting close to a loss of rank for the Jacobian, we see that many problems may happen. So, although the pseudo-inverse is defined, we will have a sudden discontinuity when we are getting closer to a singularity and then when we are in a singularity itself. And we would like to smooth the solution to avoid that the joint velocity that we generate by pseudo-inverting, like we did for the inversion of a square Jacobian getting closer to a singularity, would increase in norm. Okay? So, in fact, the technique that is being used is the damped least square. And just to make sure that we are on the same line of thought, this applies equally well to square and non-square matrices. And we find the solution Q dot to our original task velocity problem, so finding Q dot such that J Q dot is equal to R dot, by solving an unconstrained, pay attention, there are no constraints here, an unconstrained optimization problem, which is quadratic in the unknown Q dot. And this unconstrained problem has an objective function to be minimized, which is a combination, a weighted combination between what? The second term is exactly the error in velocity, in task velocity that we would like to zero, if possible. The first term instead is a weighting of the norm of the solution. With a scalar mu square, actually I modified the notation here. In the robotics 1 we call this scalar a positive lambda. Now I put mu square so I know that this is positive or zero. That combines how much we would like to keep the norm of the solution small with respect to what type of error we accept for the task velocity. So it's a compromise. It's a compromise, of course. If you take a large mu square, you tend to have a solution which has small norm, so a small velocity, but maybe you get a large error, and vice versa. If you remove completely the weighting, the damping term, so mu is set to zero, you risk to have an exact solution, but with a very large norm, because you're very close to a singularity. In a singularity, of course, you may still have a solution or not, depending on the fact that the R dot lies or not in the range space of J. Now, are you able to find the solution of this? I will not do this, but if you write down terms, this is a quadratic function in Q dot. You do unconstrained minimization, so you take the derivative with respect to Q dot and set the derivative equal to zero. This is a necessary condition for optimality. Then you see that the second derivative is positive, so if you solve this, you will find a minimum and not the maximum. And the solution takes this form. Now we are in a very good shape because we see that minimizing this problem for mu square getting to zero returns exactly the pseudo-inverse when we have full rank. In fact, if we have full rank, we don't need to introduce this damping factor. But full rank is a relative concept. We may have a singular value which is getting closer and closer to zero, so we still have full rank, but the norm of the solution will explode. This is why we are introducing mu. And when we are introducing mu, and this is a very nice property also, then we don't care about the rank of J any longer, because this matrix that we invert is given by a positive definite matrix, the identity times mu square, plus a semi-definite matrix. So the result will be always a positive definite matrix and therefore invertible. Okay? So as soon as you bring in some mu, then you can invert and you can get this solution. And this is a solution that minimizes the associated objective function. You pay a price for this. So this is a kind of a robust inversion that you like to activate when you're getting closer to a singularity, to keep the velocity small. But far from singularity, you better turn off this mu, because as soon as you introduce the mu, you will get an error. Even if the original task was still feasible. So the R dot was still in the range of J. And the error can be computed by replacing Q dot into the equation, subtracting, so into J times Q dot, subtracting R dot, and looking at the expression of the velocity error. And you see that if and only if mu is different from 0, mu square is positive, then you get an error. And of course, the error is larger. The larger is the task velocity that you would like to realize, and also the larger is the mu factor. Okay, pay attention. Here you have an inversion, so you have a mu square at the denominator, and here you have something in the denominator, but still increasing mu. You tend to have larger errors. Okay. Now, in fact, the damped less square inverse, or the damped inverse of J, is not a pseudo-inverse, and is not even a generalized inverse. Why? Because even if R dot is in the range of J, so we could realize this, it does not return a joint velocity that produces R dot. We have just seen the expression of the error. So it cannot be a generalized inverse. It cannot be a K matrix like the one that we introduced at the beginning of this lecture. Still, you can use the singular value decomposition of J, and in fact, this is what we do in our software, in all our software driving the KUKA lightweight arm and also the universal robot. We compute the singular value decomposition, and we use the same three matrices of J for computing not only the pseudo-inverse, if we can, but for computing the damped least square, which has a similar expression. You take the two orthonormal matrix, you invert the order and transpose, and you do the damped least square of the sigma matrix. And the damped least square of the sigma matrix is very similar to the pseudo-inverse, but so the block of 0 goes at the bottom, and on the diagonal you will get 0 for the eigenvalues which were 0, like in the pseudo-inverse. But here, you see that instead of having 1 over sigma I square, you will have sigma I over sigma I square plus mi I square. Okay? And in fact, if you do this with mu I equals 0, you obtain exactly the pseudo-inverse. Okay, so the decomposition gives you. So this is a small generalization of this formula. Now, there are more technical aspects. The first one is not so technical, it's very, very intuitive. So this mu square, you would like to have your software having mu square equals 0 when, by doing the evaluation of the singular value of the Jacobian, you find that the rank is there and the minimum singular value is sufficiently larger than 0. But when you realize that something is going wrong, so that you're getting closer to a singularity, you switch on the mu, and you, with continuity, get into this solution, of course, realizing some error. Okay? And then when the singularity has gone, so you have crossed in the vicinity of this singularity or even over the singularity, then you turn on to the pseudo-inverse solution by bringing back mu to 0. And there are other techniques, like this introduced by Maciejewski and Klein, that are able to do a selective solution. So not to spread the error in all directions, but trying to save, preserve, let's say, right execution at least of the components which are in the range space of J, which would otherwise be completely lost if we apply the basic DLS method as such. Okay, now to understand the difference between pseudo-inverse and damped least square, it's very nice to look at one particular direction. Now you can imagine that you have just 1 degree of freedom of redundancy, or you can put yourself into a special direction, which is the direction of one of the singular vector of your Jacobian. So along this direction, you know that you have an associated singular value. Ui is an eigenvector of JJ transpose, and this appears in the expression of the pseudo-inverse and also of the damped least square. So suppose that you're now looking what happens to your velocity, norm of the velocity, when you're moving in that direction, and when the singular value in that direction is getting closer to 0. So it's getting singular, in a sense. Okay? And here it is, you have a plot. The blue, so the sigma is 1. 1 or 100 doesn't mean anything, it's just positive. And now you're looking at the norm of the solution using the pseudo-inverse, so the blue line, when this sigma is getting closer to 0. And in fact, you see that the inverse of the pseudo-inverse of a sigma, which is positive but small, is always 1 over sigma. And if it's small, then this goes to infinity. Only if sigma is exactly 0, so when you are in the singularity, the pseudo-inverse returns a 0. So you have a discontinuity in this sense. So getting closer to the singularity, the speed in that direction increases, and when you reach 0, then you return to 0. There's a point here which is not shown in the graph because it's just a point. On the other hand, the damped least square does the plot in red. So when sigma is still large and you're introducing some value mu, then the two solutions are practically the same. And now for the same value of mu, when sigma is being reduced, you see that the norm of the velocity increases but does not go to infinity. It reaches a maximum and then smoothly goes down to 0. In fact, if you compute, if you do a simple study of the expression of the damped least square velocity in that u direction, so you have a function f of sigma, which is sigma over sigma square plus mu square, and you want to study this for sigma going to 0, so you take f prime of sigma, which is df over d sigma, so this is the square of the denominator, and then you take the derivative of the numerator times the denominator. The derivative is 1, so you have sigma square plus mu square minus the numerator, sigma, times the derivative of the denominator, which is 2s, so minus 2s squared. So the result of this is mu square minus sigma square over sigma square plus mu square square. And in order to find a minimum or a maximum, you set this equal to 0, and this gives you exactly sigma over equal mu. So at sigma equal mu, you have in fact a maximum. And the maximum, if you substitute sigma into this expression, so for sigma equal m, the function is mu over 2 mu square, so it's 1 over 2 mu. So with choosing the mu, you know what is the maximum norm that you would like to tolerate in the direction of an eigenvector associated to the singular value, the smallest one that is going towards 0, and you can shape the solution in this way. So you see that at 0, so in the singularity, or when sigma is very large, the solutions are exactly the same. The behavior is different while approaching the singularity. Now, this is quite technical, I understand, but I hope that, this graph suggests really what's going on. I have another geometric interpretation of this, which may be even more suggestive of what's going on. So suppose that you have, again, I have to work on the plane where things can be drawn easily. So I'm assuming that I have two joint velocity, so n is equal to 2, and I have only one task. So I have one equation, j q dot J1 q dot equal R1 dot, which is a line in this velocity space. So all the points on the line are velocity which satisfies the task at the velocity level. And if I'm taking the minimum norm 1, I will take this solution, which is the closest to the origin. Now, suppose that I add a second constraint. So I'm squaring the system in this case, but I could not do better than that. So if the two constraints are linear independent, so I have full rank for the J, these two equations characterize one intersection point, and this is the unique solution. You're inverting the Jacobian, which is square. First row is J1, second row is J2. Okay? So your solution is here. But what happens if the second constraint tends to let the Jacobian become singular? So it's almost aligned with the first one. So this was the original one. The second one is not parallel, so we are still non-singular. We still have only one solution, which is at the intersection of these two lines, far away somewhere. So with a large norm. And if you're computing the pseudo-inverse, you will get that solution. Instead, if you're computing, you're introducing a damped least square, probably your solution will be somewhere here, which is close to both equations. So you're approximately solving your task, but doing an error in every direction, in fact, but with a norm which is much smaller than this one. And in order, this was a qualitative picture, so I decided to make some quantitative analysis here. This slide is, well, we can flow over very easily. So I have a planar to our arm. Let me draw the situation with unit length, and I place this in an almost singular configuration. So I have 45 degrees for the first joint, and if I had 0 for the second, this would be a singular configuration. Okay, but in fact I'm giving 1.5 degrees, so the arm is almost stretched. Okay, and now I'm giving a desired velocity. The desired velocity is exactly in this direction. R dot has unit norm is minus 1 over square 2 and 1 over square 2. And pay attention, even if I were singular, this is exactly in the range space of J. So it's a velocity that I can execute despite I'm singular. Of course, I cannot invert the Jacobian here because I'm in singularity, I cannot invert it. Close to singularity, I will get anyway very large joint velocities for executing exactly this R dot. And those large joint velocity may not be executable by my actuators. So the excess solution would be this one, if I'm not introducing any damping. There is a solution in singularity and also close to singularity. Now, suppose that I'm formulating my damped least square problem. So I would like to find another q dot, possibly close to the exact solution, but minimizing or keeping low, let's say, also the norm of the velocity itself. So here is the picture. On this axis, you have q1 dot. On the other axis, you have q2 dot. And the origin is there, 0, 0. And the exact solution is here. And these two lines, the violet and the light blue one, are in fact the two constraints. So I'm with mu equals 0, or very small. With mu equals 0, I'm getting exactly this solution, which is very far away from the origin, so has a large norm. Although it's 1, 1, it's large relatively. So if I'm introducing mu, I will get a solution which is out of the intersection, which is the exact solution, is somewhere in between the two lines. And for instance, for mu square equal 10 to the minus 3, I will get a damped least square solution, which is 0.47 for the first joint velocity and 0.05 5 for the second joint velocity, which has much less norm than the 1-1 solution. Okay? And if I increase farther mu, then my solution will abandon this nice position between the two constraints and will get closer and closer to the origin. But of course, the error will increase accordingly. So this is another picture of the same type. For instance, if I take mu squared equal 10, not 10 to the minus 3, you see that my solution is the blue one there, closest to the origin, with norm very small, but with a very large error. In fact, I have a table here that summarizes this numerical study. So with mu 0, I'm getting the pseudo-inverse. With mu positive, I'm getting a damped least square, and I'm damping and damping my solution more and more. Okay, and the two pictures that you see are for 10 to the minus 3 and 10. And if you compare the norm of the velocity solution and the norm of the velocity error, you see that with the exact solution, the solution is 1 minus 1, so it has norm square 2 and no error. So a large value and no error. If I start increasing the damping factor mu, for instance, to the 10 to the minus 3, I have an error which has increased. It's still 10 to the minus 2, but the norm has reduced considerably. And this continues to reduce, but in fact, the error increases, and those values, especially this one, starts to be unacceptable. Okay, so you're damping too much your solution. So, this concludes the first class of methods, and with some variants. There are something that we should comment on this. First of all, there's one concept that we should really understand deeply. The fact that we are minimizing joint velocities, so keeping velocities small, weighting, damping, and so on, does not mean that we will eventually have an explosion of velocity because we are getting to a singularity. Okay? Because our methods are purely local. They are taking a decision now without predicting what type of task I will need to execute down the road in my trajectory. And probably by making the best choice now, this will be the worst choice in the future. Okay? So minimizing joint velocity may not avoid an avalanche problem where all of a sudden I need very large velocity to execute the task. This is one problem. The second problem is a more subtle one that requires really some topological study. So I will skip this, but just to mention this phenomenon. The phenomenon is the non-repeatability of cyclic task trajectories. So suppose that you have a 3R robot and your task is going around this square several times. So you start with a given configuration, you command whatever generalized inverse, so I'm really not saying a pseudo-inverse, a weighted pseudo-inverse, whatever you choose, but it should be at least a generalized inverse. So this generates a Q dot, you integrate over time, so the configuration will be computed in this way. And while doing the circle, at some point you will end up after one tour, and the final configuration that you have reached typically is not the one that you started with. And if you do a second tour, you will find at the end another final configuration, and another, and another. Remember, there are infinite to one possible inverse kinematics for that position. So it's not something that you will end up with. And this is a problem. Why? Because if you have a constrained workspace and you're setting up this task for your robot, and your robot is redundant, and you're using, for instance, pseudo-inverse thinking, well, nothing will happen, slowly you may have a drift, and you may collide with some object which, after the first few rounds, was far off the structure. Okay? I have a nice simulation here where we have the KUKA 7 degrees of freedom robot doing some cyclic task under pseudo-inversion. So the Luca is mounted on the table. You may see or not see a circle here. Its end effector is doing around here. So in the vicinity, there's a human operator, which does not move. Let's say, reads a newspaper or whatever. So we command the cyclic path. The path is only specified in position. So the dimension of the task is 3. The dimension of the joint space where we choose the velocity is 7. So we have a 3 by 7 Jacobian. We may do pseudo-inversion, for instance. And the robot will start execute. It does one circle, and there's no collision. A second circle, same second circle, and no collision. And then, quite at the end of the third circle, the drift will let collide, and you see we change the color into a pink color to signify that this would be a dangerous situation. Okay, and this is exactly the drift phenomena related to Jacobian-based method when they do not guarantee repeatability. And if you want to impose repeatability over cyclic task, so return to the same configuration every time you complete a cycle in your task space, then you have to modify your technique. Either compute it globally or impose some special properties of integrability of your solution.